Okay, today we're going to begin deriving expressions for the thermodynamic basis functions, and we'll begin with the simplest one, which is the internal energy, U, which is defined as an average of the total molecular kinetic energies plus the total molecular interaction potential energies in the system. And the average is done over the equilibrium distribution function, and then the integration is carried out over all of momentum and configurational space. And we have to normalize this since it's an average. And we recognize the denominator of this expression as simply the normalization factor n factorial for indistinguishable particles. So this is the fundamental definition of the internal energy, and it's applicable to both equilibrium and non-equilibrium systems. And for non-equilibrium systems, we simply would use the density function Fm, appropriate for non-equilibrium systems. But let's see why this is called the internal energy. So by internal, if we look at the momentum, here we used a prime to denote that the momentum of any ith molecule in the definition of the internal energy is the absolute momentum p sub I relative to any bulk motion, which we could denote as mv0, where v0 is the bulk velocity in the system. And for a system at equilibrium, V0 is indeed 0. Which we've seen in the derivation of the equilibrium solution to the Liouville equation. So the kinetic energy that we wrote as for any molecule is relative to any bulk motion. So again, that helps define what we mean by the internal energy. In other words, we're taking away any external contributions associated with any bulk motion. In addition, you notice that we've only included the interaction energies between the molecules. So the definition of the internal energy, again, does not include any external potentials, such as gravity or other external forces that may be acting on the system. So the definition here is clear that we're only to include the kinetic energies of the molecules relative to any bulk motion, and also the interaction energies between the molecules, and do not include any external potentials that may exist in the system. Now, the first term in the internal energy involves the kinetic energies. And we can substitute in the equilibrium solution to the Liouville equation. And you recall that that solution is the separable solution in terms of a momentum space part and a configurational space part. So the argument then of this integration only includes momentum contribution for the first term. Therefore, we can integrate out the configurational part, which will give us an n factorial that will cancel with the coefficient 1 over n factorial. And so all that remains to be done then is carry out the momentum space integration. And so we know that this is the Maxwell-Boltzmann distribution in the molecular velocities. So this integration, which goes from minus infinity to infinity over all momentum space, can be carried out quite easily, and the result of all that is the simple ideal gas result for the internal energy as 3/2 nkt, where n is the total number of molecules, k is Boltzmann's constant, and T is absolute temperature. So this integration step has been assigned to you as your next homework, and again is very straightforward to carry this out, and the result is quite familiar to you. And we can proceed on now to looking at the configurational part of the internal energy. So we have then the internal energy has the first momentum space integration, which is simply nkt, and then the second term we end up with the integration involving the interaction energies, and for again the equilibrium solution we can put in our separable function, and now the argument associated with the integration is simply involves the configurational part. So we can use the normalization condition on Hn to simplify the last term and now this is the general expression for the internal energy of any fluid at equilibrium, and it also includes a solid phase as well. So any gas, liquid, or solid system follows this functional form.